Howdy, we're the telemed team for Endeavor. I'm Angel,
And I'm Michelle.
and let's get into more information about us. So I go by Andrew, and this is me on the left. I'm a senior in electronic systems engineering at Texas A&M, and my hometown is Richardson, Texas.
And I'm Michelle Nguyen. I'm pictured on the right. I'm also an electronic systems engineer at Texas A&M University, and my hometown is Houston, Texas.
All right, so starting off, we're going to be answering why we joined Endeavor. So personally for me, I was looking for experience and personal development in my skills in systems engineering, as well as software development. I looked at a lot of projects from Endeavor previously. I noticed there was a lot of opportunities for both community engagement as well as networking with their autonomous vehicles and telemedicine projects. So I looked at all those factors and decided, hey, I want to join Endeavor and just go for the ride.
So the reason why I joined Endeavor was partly due to my physical status as a person with diabetes. During COVID, I had to experience a lot of telemedicine visits, virtual visits with my doctor online. And after talking with Dr. Lee, I learned about his telemedicine team and his Endeavor Ride program, which actually is an autonomous vehicle that serves people in the community of Nolanville and provides them with telemedicine services on board. And so learning about this opportunity sounded very good for my career development, and also as a great chance for me to volunteer, form some community engagement, and also work on my networking skills with people who are both in and outside of my major. So Endeavor's mission statement. Endeavor stands for envisioning the neo-traditional development by embracing the autonomous vehicles realm. They are a 501c3 nonprofit organization dedicated to future-proofing small communities by enabling them to become smart cities. Basically, they help small communities to utilize emerging technologies such as autonomous vehicles and AI to accomplish desired socioeconomic, environmental, and health outcomes. In 2018, Endeavor was launched as a pilot project sponsored by Texas A&M University and the WM Keck Foundation. Its foundation is an interdisciplinary smart city education that empowers young people to see creative, affordable, and effective solutions for challenges faced by underserved communities and underprivileged populations. The success of Endeavor is built upon trust and partnership among educators, students, industry, and local communities. So our part of that vision was to create a system to transmit biometric readings directly to doctors, to engage with the community, to discuss plans and future developments with the team, and to provide our fields of expertise for a potential multidisciplinary team. So the system we decided to start off on was the blood pressure monitor. Of course, there were other sensors we could have worked with that Dr. Lee suggested, like a temperature sensor, but we decided that we wanted to pursue a blood pressure monitor as the system was already in development prior to our joining, because it was the most complicated system to unravel, and that because it would provide the best learning curve for future devices. So what can the system do? It can read in air pressure from hardware and interpret it as blood pressure. It uses an algorithm to convert PSI to millimeter mercury and has pressure data displayed on an .xls file. So after our first semester, some things that we learned were pros were that the project was closely tied to our major, that we learned what the different components were used in and on the market BPM. We gained familiarity with each other, increased teamwork skills through team bonding activities, and we increased how comfortable we were reaching out to professors and industry professionals. Some cons we learned were that the chosen BPM system that we wanted to analyze had checks to prevent product replication. So this also added concerns of future legality issues, and we lacked an electronic data sheet, which greatly decreased our progress this semester. But some lessons we learned were that a self-created BPM would resolve potential legality issues and provide us with more control and knowledge of the system. We actually have some professors who previously worked on or done research on medical devices. We also learned Dr. Lee's ready to support us with whatever we need and that we make a good team with our diverse backgrounds. So based off of semester 1, we started planning for our second semester with Endeavor. And so this semester focused more on research, hardware, circuit, and software.
All right, and I'll be talking about the rest of these for now. For the researches, we found standard hardware designs from the blood pressure monitor in our first semester. So we looked at how we can take apart several different blood pressure monitors and see that they have 3 major hardware components in them throughout each sensor that we find or look into. So going into research papers, we also noticed that this is a standard for what is needed for a blood pressure monitor, the 3 hardware components, which I'll discuss later on. We also looked at possible ways of gathering data. So what we have currently is one of 2 major ways that they are going to plot and interpret the data, but we do need 2 in which to acquire systolic and diastolic. We looked into how these signals are calculated or taken from circuitry. And so far we have completed 1 of the 2 in perfect repetition. So we also learned to interpret data from given signals, and that's going back to possible ways of gathering data. And we noticed that we're able to automatically get a transducer, for example, that already is pre-digitized. So we noticed that there were similarities to other people's designs, and we decided to get an alternative that pre-digitizes our data, which you'll be seeing in the hardware section later on. So a couple of milestones that we would like to talk about. We were able to develop hardware and circuits through these researches that took place. We improved the circuit and were able to get raw readings from the hardware. And the development, we developed a stable process of how to read blood pressure. Now, these will be the hardware components that we're going to be talking about. So the main components are the DC motor pump, the air valve, and the pressure sensor. Let's not forget the pressure cuff, but that would be not the electronic part. So for the DC motor pump, the process of this is basically that the pump will begin inflating the pressure cuffs while the valve closes to cut off air from leaking. And within I'd say some tubes, the pressure sensor will read the environmental pressure inside that tube in order to get a reading from the pressure sleeves. Now, we tried to keep this as cheap as possible in order for this to be replicated for other third parties. So as you can see here, that the most expensive one would be the pressure sensor, but the rest of the components are not bad individually.
So now I want to talk a little bit about the case that we developed for this hardware. So using CADing software, SolidWorks, we were able to design a case for our system that has room so that future system would be able to be applied on top of this system that we have currently. The prototype filaments we used were PETG and PLA. We had some difficulties with the first filament, so we ended up using the second filament, PLA, a lot more. Unfortunately, the lapse time printing currently is about 26 hours. So we're looking to redesign and reduce the printing time in the future.
Now for our circuit. So what we have here is our MCU microcontroller, the Arduino Uno. So this is used for embedded systems code that is going to be toggling our electronic components, the valve, the motor, and also reading in the data from the pressure sensor. And on the right side, we can see our circuit design. The circuit design consists of 2 analog pins and 1 I2C communication pin. Now, the two analog pins are used to toggle both the motor and the valve, while the I2C is going to be taking in sensor readings from our blood pressure sensor. Now, on the right, the very right, you can see the image of the connection between the circuit as well as the microcontroller together. So you can see how everything is connected, and you'll also notice that there are a lot of wires within development. Now, for the most important part was our software. So in our embedded programming design, we had 5 major topics to talk about. The fact that it is an Rtos code, it is using Rtos coding, which means that it is specifically formatted to be used, and it will be able to add on newer tasks for later development. Rtos code basically means that you can run several different functions at the same time without them interfering with each other. So it's as if they were working simultaneously, but in actuality, everything is just taking their own individual fraction of time in microseconds. So for data conversion, we're able to use the code that Adafruit, the company that created the pressure sensor, provided in order to convert the data, the digitized data, into PSI. So for our code, we learned to convert the PSI into millimeter mercury. And that goes to our next topic, the data transmission. So once we get the millimeter mercury, we're able to send that data into the computer that's connected with our MCU, as you can see in the bottom middle. It's using comm communication, and the computer is going to access that communication port in order to acquire that data. And that is where our 4th point belongs, where we're basically using the computer to communicate with our microcontroller. So number 5 is a little bit related to the first one, Rtos code. It is a task-based system, and it will run with several different tasks that will basically work at the same time. Now, for this, what I want to talk about that's different from Rtos coding is the fact that because it is a task-based system, we're able to layer on more tasks for future devices. So we're able to incorporate other systems with ease. Now, on the right, you can see our resulting code and our graphs that we've acquired throughout our project. Now, the y-axis is the pressure in millimeter mercury, and the x-axis is going to be iterations, which is basically the number of times it has recorded the sensor. So you can think about it as basically time. Now, the overall capabilities that we have for the software is that it senses pressure, actuates the motors, and also translates the data. So how does this work? So the user sends the signal from the computer to the microcontroller to read the blood pressure monitor. So what would happen is that we go into our COM port, we type in go, but later on, we're probably going to be adding more complex commands to it. Now we have go since it's only one system. We type in go, and that information gets sent to the microcontroller. So the microcontroller gets that information, and it's going to do a series of functions. So for starters, the motor will pump air as the valve closes in order to inflate the blood pressure cuffs for the patient. So that will be for the microcontroller to toggle those electronic parts. Now, for the algorithm, basically, it's going to constantly transmit data as the cuff inflates. So whenever it finds a max value, it's going to stop the inflation of the cuffs. And after a certain point, it's going to start rapidly deflating. At the same time, because this is an Rtos program, it's still taking in the readings of the data. So as the analog pins stop, you're still getting consistent readings that will get transferred into the computer. So with that information, the microcontroller is toggling the electronic parts to end the task, such as stopping the motor from pumping and opening the valve. With the data that's collected, we're able to translate that information to millimeter mercury. And then with all of that data that we've gathered, we're able to put it on a graph and plot it, all within a span of 2 minutes. So resulting from our second semester at Endeavor, we have created a fully functional blood pressure monitor with transmittable data that is able to integrate future devices later on, as well as a strong system foundation that we're able to use consistently for future developments. What we have for the blood pressure monitor at the moment is that it plots, the plot shows a full reading of someone's blood pressure. The data transmitted is through the COM port, so we're able to get the data onto a computer online afterwards, with improvements to come, because what we have so far is only half of the graph that we need in order to finally get systolic and diastolic.
So to wrap up, the second semester, the pros we learned were that we develop foundational code and hardware, we create a fully functioning system that can transmit data, the system follows correct BPM monitoring processes. Some cons that we found were that the system does not have proper readings, but gives a graph instead. There are wire connections that are so loose and require additional tension and soldering. The case requires updates to reduce print time and improve print quality. Most importantly, the lessons we learned were that when researching blood pressure algorithms and logic, doing that first is more important than neatly inspecting hardware functions due to the different methods involved in finding the desired results, such as systolic and diastolic blood pressure. We learned that Dr. Lee is still ready to support us with whatever we need, and that we make a good team with our diverse backgrounds and individual skills. Thanks for listening.
Thank you for listening.